Alright, so the second engineering analysis that we performed was designing a circuit that would enable us to control our valves using a digital output. In order to do this, we looked at the specs on the valves and determined that we would need to supply 12 volts at around half an amp per valve, meaning we needed to supply 3 amps total for our 6 valves. In order to do this, we researched part specifications and used Kirchhoff's voltage law to determine the circuit components that we would need to supply this kind of current and voltage. This is the result of our analysis. We have the power supply here putting out 12 volts, which leads into the upper end of the diode as well as one of the terminals of our valves. This is connected in parallel with the other terminal of the diode and the other terminal of our valve, which leads into the source of our transistor here. So this transistor basically blocks the flow of electricity until we supply a digital input to its gate, and then it opens up and allows the circuit to be completed, which opens the valve. The diode's purpose is to protect the solenoid coil, and we decided to use the transistor because it had a much faster response time than the mechanical relays we were originally looking at. And our analysis actually allowed us to move to just using the power source on the board itself, because we had moved to 12-volt valves instead of 24 volts. So we were able to eliminate one further component through our analysis. And this is what allowed us to construct our full circuit with minimal time delay in order to meet our specifications.
For our project, one of the main engineering analysis we performed was an analysis of the pump. We wanted to make sure the pump could sustain the flow rate coming out of our valves, and we also wanted to make sure the pump could pump the water to the top of our frame. So the two main things we calculated were the total head that was necessary in the system, and also the flow rate that would be coming out of the valves if all 6 of our valves were open. To calculate the total head that was necessary, we first calculated the Reynolds number of the water coming out of the valve. From that we could determine if the flow was turbulent or laminar, and from that we could calculate the total friction loss in the system, which allowed us to calculate the total head. For the flow rate, what we did was we calculated the velocity coming out of the valve and also the area of the valve, and then multiplied by 6 for our 6 valves. This gave us the total flow rate. Our results were we needed a head of 6.55 feet and a flow rate, and the flow rate was insignificant because any pump that we found that sustained a flow rate or that sustained a head of 6.55 feet, it could sustain a flow rate much greater than what we calculated to be necessary. This was significant because it allowed us to switch to using larger valves that had a more substantial flow in the project. For the codes and standards, the main codes involved in the pump were just to make sure that none of the electrical outputs approached or ever came into contact with the water that the pump was pumping.